Live. Okay, let's talk about the homework. First question, drawing one time from the prior predictive distribution. So draw from the distribution of the parameters, draw from the conditional distribution of the data you anticipate seeing, which in this case is independent normal distributions, conditional on that realization of sigma. And then you can plot them, which is what I did on the next page here. Ordinarily, we would take a lot of draws from the distribution, prior predictive distribution, and probably have to do this with some more sophisticated form of plot, but this is a plausible representation of what you think your darts might look like, and if you did more repetitions of this process, you would see a whole distribution of where you anticipate your dots to land before you throw them. So then with that information in mind, the second problem is to derive the posterior distribution, and a lot of people had more trouble than they should with the likelihood part of this function, which looks like just this, and I've given you some pseudocode for that. But the thing to keep in mind is that the likelihood function is a function of the parameters. In this case, sigma, or you can think of it as a function of p, but there's a one-to-one mapping between p and sigma, so you can think about it either way. But if the likelihood function is a function of sigma, for each sigma, there should be exactly one real number that results from it, because a function has to be a unique mapping from one input set to exactly one member of some output set. So a lot of people found themselves with, it was producing like 50 numbers or 100 numbers, or it would produce one number for the entire PVEC instead of one number for each element of PVEC, which is what you need in order for this to be a one-to-one function. And the thing that people were struggling with was the fact that because the x and y coordinates of these dart throws are conditionally independent given sigma, in order to calculate the ex ante probability of the observed data as a function of sigma, we need to multiply those contributions together, except they're small numbers, so it's better to take the logarithm of the normal density function, evaluated at x and y, add all those together, and then exp the result at the end in order to get the joint probability in the numerator. So one number for each element of PVEC. Integrate that from 0 to 1 over the space of p in order to get the denominator, which will be some real small number. And then you can plot the ratio of the numerator to the denominator. It'll look something like this. So again, this is the posterior distribution of f of sigma. It's not necessarily the thing that you most want, which is the posterior distribution of sigma, but we'll get to that. But the important thing you can see here is the contrast between the posterior density and the prior density. Both the black line and the red line have an area of 1 underneath them. But by conditioning on these 50 x and y coordinates, we've reallocated all this area over here and all the area by 1 under the prior into a much more concentrated density function around 2/3 or something like that in the case of the posterior. So conditioning on data reallocates credibility from prior to posterior. So that is the Bayesian approach, and it would have pretty much worked fine if the x and y coordinates were observed. You get a lot of information about sigma from a relatively small number of dart throws if you actually measure the x and y coordinates, but no one does that, and so that led Tibshirani and the other people he co-authored with to try to figure out a way, well, how can we estimate sigma just from the scores, the integer values that the dart thrower obtains. So we need the score function, and then the next problem was to evaluate the sampling distribution of the estimator of sigma conditional on the actual sigma. and to do this with simulations. And so this function, in addition to S, the number of simulations to do, and the number of dart throws to obtain, takes sigma as the argument. You have to pass it in from the outside. Everything that comes out of this function is conditional on the true, or at least the assumed, value of sigma. But it's basically a similar process, except you're not drawing from your prior distribution of sigma anymore. You're just conditioning on the true sigma, drawing data, x and y coordinates, converting those to polar coordinates, the radius and the angle, calling the score function for each radius and angle, and then using this expectation maximization estimator that they have in the darts package in order to estimate sigma. So what is the conditional distribution of this estimator of sigma that only utilizes scores conditional on the true sigma, which, like I said, it's a little bit weird to think about, setting up this whole thing conditional on the truth when you don't know the truth. But assuming sigma is 46, we can get a plot of the sampling distribution that might look something like this. It's kind of jaggedy in both the CDF and the PDF due to the discreteness of the scoring function. Some values of the scoring function are not possible, and even then only integers are possible. So that makes it not as much information, not as smooth, need more observations in order for this to work well. But the fundamental aspect of it, it's pretty spread out. If your true sigma in this case is 46, well, there's a decent chance you could estimate something closer to 30 or closer to 60 as a result of those 50 throws. So it's not a very concentrated sampling distribution for this particular estimator if you only give it 50 scores, and it's also slightly biased, not a whole lot. So the average is about 45, but that's pretty typical for maximum likelihood estimators with finite sample sizes. And so they didn't really go into that much in the short paper, but it's not a great sampling distribution with the limited information that the scores provide. Good so far? Okay. Next question was about, well, in the documentation, it says, I made these 100 dart throws. Tibshirani is the package maintainer, but there's reason to believe those dart throws may have been actually thrown by his roommate, Andy Price. So we can test the hypothesis that it was those 100 dart throws were thrown by Tibshirani by setting sigma t to 65. Alternative hypothesis that they were thrown by Price, set sigma p to 27, and we need to calculate a log ratio statistic in order to do, or the ratio, log likelihood ratio statistic in order to conduct this hypothesis test. And to do that, you need to figure out what is the distribution of the likelihood ratio statistic under the hypothesis that these were thrown by Tibshirani and they used 65 as the standard deviation. I did not get a lot of questions about this on CampusWire, which probably means you screwed it up. But it is a related procedure where you repeat this, S times or whatever, draw 100 x and y coordinates, convert them to polar coordinates, apply the score function to those, then calculate the estimator under the assumption that sigma is from Tibshirani and get that log likelihood. Subtract the log likelihood that would be obtained assuming sigma is from Price. The difference of those is the log likelihood difference, and if you EXP those, then you get a likelihood ratio statistic under the assumption that sigma t is what's generating this. But you get this null distribution of the statistic, and then you can compute the value of c such that there is a 5% chance that you reject the hypothesis that Tibshirani threw these when Tibshirani, in fact, did throw them. And that cutoff is about 1 million. That gives you a 0.05 on the vertical there. So this is the distribution of the likelihood ratio statistic under the null hypothesis that Tibshirani threw this. Then we can take the actual scores, calculate the actual likelihood ratio statistic, see whether that is less than our cutoff. That's true. So we reject the hypothesis that Tibshirani threw these darts in favor of the hypothesis that Price threw these darts, assuming those are the only two possibilities. Now, fortunately for you, this lambda was so small that you would probably reject it even if you miscalculated what the C should be. Like if you calculated any positive number for C, you're going to reject this hypothesis. But the correct way to calculate the C is by deriving the null distribution and then seeing what's the 0.05 quantile of that to get your cutoff value is about 1 million. Question?
Really, a lot of times these get left in log units, right? It's the same thing. It doesn't actually make a difference, right?
Log ratio difference, and then the cutoff would be some different number, but you would still get a 5% rejection rate when the hypothesis that Tibshirani threw these is true. And there's a lot of stuff where people try to derive these things analytically. I don't think it would be possible in this case, but it's easy enough to do with repeated simulation on a computer. Okay, last problem, almost the last problem on the first one is to calculate the posterior distribution by prior predictive distribution matching. This also took longer for people to write the code than it probably should have, given that we did 2 examples of this already that you just had to modify to be appropriate for this data generating process. And then there's the additional thing that, well, if you took all 100 or 50, whatever, 100 dart throws at a time, the denominator in Bayes' rule would be so small that you would always reject. So we have to do this 1 dart throw at a time, in which case the denominator of Bayes' rule is really small still, but you have like a 1 in a million chance of getting a match, and so it can run in a fairly reasonable amount of time. So if we want 4,000 matches for the posterior distribution on each dart throw, we loop over those, so looping over the scores, initialize sigma and set S to 1, then do a while loop where we repeatedly draw from the prior distribution of sigma, then use that sigma to draw once the x and y coordinate from normal distributions, then convert those to a radius and an angle, calculate the score based on the radius and the angle, and if that exactly matches the nth score that we observe, then stick the proposal for sigma into our storage for sigma and increment s to the next thing. Eventually, you will get capital S matches. So capital S draws from the posterior distribution conditional on the first n throws. And when that's done, we want to update our prior into our posterior distribution by calculating the quantiles of those 4,000, the median, the lower quartile, the upper quartile, to create a new what I think, which is in turn going to be used the next time we go through the loop in order to draw from the prior distribution of sigma. So we're drawing from the prior distribution, drawing from the predictive distribution, seeing if we can get a whole bunch of matches. Do that until we get enough draws for the posterior distribution, conditional on that dart, and then use that posterior distribution to form the quantiles for the prior distribution for the next dart. And so if we loop over all the darts, the final posterior distribution that we get at the end will be conditional on all 100 dart throws, and it looks like that. Still has a considerable amount of uncertainty. It's smoother than the sampling distribution of sigma from the frequentist perspective, But anyway, that's sort of what we have based on our initial beliefs, which were actually about your ability, and then conditional on someone else's, probably Price's, darts throws to sort of update those beliefs into a posterior distribution. So does anybody have any questions about what's going on in this while loop? All right. So that's really, the main thing, even though we're not going to be doing prior predictive matching very much anymore going forward, it's still good to know how to draw from the prior predictive distribution in order to be able to evaluate the implications of your prior when they're not obvious. So kind of the point of this article by Tibshirani was then to say, okay, given this point estimate of sigma, there's another algorithm in the package that can tell you where you should aim when you're playing darts, given your sigma, which basically represents your, lower values represent better ability to throw darts more precisely. And so it's easy enough, numerically at least, like there's an EM algorithm and whatnot to do it, to find the optimal aiming point for a given sigma. But the fundamental difficulty here is that no one knows exactly what their sigma is. No one knows what their true sigma is. Even if they play darts a lot, they probably couldn't tell you what their true sigma is. And yeah, you could estimate it really accurately if you measured the X and Y coordinates. But if you just measure the scores, then the sampling distribution of the estimator of sigma has a lot of variance to it. Even if your true score is like 45 or whatever, you could easily get an estimate of that true score that was like 30 or 60. And so this idea of, well, take a point estimate of sigma, plug it into this thing, and it'll tell you where to aim, does not take into account the uncertainty that you have as to what your true sigma is, even after having estimated it. And with maximum likelihood, something like this, you can show that the distribution of the point estimator across people is like decent or whatever. And so consequently, on average, when on average across people, when the thing subsequently tells you to aim here, that is decent averaged across people. But there's not a whole lot to be said for this procedure for a particular point estimate of sigma and a particular derived conclusion as to where you should aim on the dartboard as a result of that point estimate of sigma, because the estimator of sigma is so noisy and you're not taking that uncertainty into account. And so that is, I think, one of the sort of fundamental places in which frequentist approach to things gets weird. They've set everything up about probability distributions conditional on the true parameters, given sigma. But you don't have sigma, so you have to come up with some estimator of sigma, and then you proceed as if your sigma hat is the true sigma without taking into account the uncertainty that the sigma hat could differ a lot from the true sigma. And there's a lot of claims and conclusions and stuff that on average the point estimator of sigma is good or at least decent or at least known, but for any particular sigma hat it can be bad. It's just the bad low ones average out with the bad high ones. But from a Bayesian perspective, we don't want to find the optimal aim point for one draw of sigma or any particular sigma, but across the whole posterior distribution of sigma, based on 100 dart throws or whatever. So you can take your posterior distribution and find the optimal aim point, for all 4,000 of those draws that you obtain from the posterior distribution of sigma. And now you have a posterior distribution of optimal aim points. And the question we're now answering is not what is the optimal place for you to aim given your true sigma, but what is the optimal place for you to aim given your beliefs about sigma, your posterior distribution of beliefs about sigma. And if you plot it out, the distribution of the optimal aim points again has a distribution that varies considerably. If you're at the low end of your posterior distribution of sigma, then you want to basically be aiming in the 19 wedge and trying to get it in the triple multiplier band. But if you're at the low or the high, the bad end of your posterior distribution of sigma, then it's telling you like the best place for you to aim is kind of in the middle of the 7 wedge, because you're so bad at darts that if you aim in the middle of the 7 wedge, you'll often land in the 16 or the 19. You're not going to land in the 7 that much if your sigma was, pretty high. In the middle, like in the kind of bulk of the posterior distribution of the optimal aim points, then it's, more in the 7 area, but closer to the triple band there. So, averaged across the whole posterior distribution of aim points, someone who has this posterior distribution of sigma should, probably be, aiming, in there somewhere on average. So we've changed the question a little bit, but we've gotten what I think would be a more realistic answer if you're trying to win a dart tournament and you're not very good.
We eventually, I think it's one of the arguments for having the Tibshirani's algorithm or being sufficient is that over enough number of games, it cancels out and you get like the sigma is actually good enough. And also like when we iterated one dart throw at a time, it was just like it's a smoother CDA, but it did not fundamentally change shape or anything else. So is like how much better is this result in the example?
If you fed 1,000 dart throws to Tibshirani's estimator, it would have been a lot better because the sampling distribution would have been a lot more concentrated with 1,000 dart throws. But likewise, the posterior distribution would also be a lot more concentrated with 1,000 dart throws. What I think is the important thing here is when you're trying to decide, well, what's the optimal thing to do given that I don't know the parameters? The optimal thing to do is not to take a point estimate of the parameters and then feed that to some other thing about making the decision, completely ignoring the uncertainty around that point estimator. The correct thing to do from the Bayesian perspective is to put the whole posterior distribution into the optimizing thing, get a distribution of optima and average over that to get the average or to get what gives you the highest expectation, not given your true sigma, but what you believe your true sigma to be based on the posterior distribution, conditional on however much data you have. Now, if you were a professional dart thrower or wanted to train to be a professional dart thrower, you should probably not mess around with the scores. You should actually measure the X and Y coordinates of your throws in order to get an even better estimate of your sigma. So there's lots of things that you could do that would be better than what it says to do in a 3-page article in Significance. But among all those things, you're still going to have posterior uncertainty as to what the true parameters are, and you need to take that into account instead of ignoring it all when you calculate one point estimate and then go with it. That's the main thing. And that's just what's fundamentally weird about the way frequentists have set things up, where everything is conditional on the true parameters that you don't know, instead of the Bayesian approach where you're saying, okay, there's beliefs about what I don't know, but I'm conditioning on the data instead of integrating over the data. So there was no 1.7 question, but I wanted to tie together some of these different perspectives on the frequentist and Bayesian approach to quantitative methods. And there's actually multiple frequentist approaches, and there's a ton of different Bayesian approaches, but they all involve the posterior distribution, so they have some similarity to it. So if we go back to Fisher, and again remember that Fisher was thinking primarily in the context of agriculture experiments, and it'd be kind of crazy or a coincidence if Fisher's framework for things would be as appropriate for agriculture experiments as it is for social science, even though social science wasn't invented until much later. But so Fisher, thinking about experiments, okay, you have n observations, you want to put half into treatment, half into control group, and even for a small number of observations, there's billions or trillions of different ways that you could do so. Let's call that all those ways little n. And you can calculate for each of the n ways to put capital N observations into two groups, what is the average difference in mean outcome between those two groups. And there's a billion different ways to calculate that, because there's a billion different ways to even put all of you into two equally sized groups. But all the different ways that you can divide into two groups and take the average difference in average creates a distribution of differences. But under the strong assumption that the treatment has absolutely no effect on anybody, then though that distribution of differences and averages should be centered on 0, and it should differ only randomly from 0 across all the billions of different ways that you can put a fixed number of people into two groups. And what Fisher advocated was saying, okay, basically when you randomly assign treatment and control, you're taking one of those little n ways to divide them into two groups, and you can calculate one of those average or differences in average, and you can see how far into the tail of that distribution across all n group differences your one estimate falls. And the proportion of those n differences that is more extreme than the one difference you observe for the one actual assignment for treatment and control that randomly happened is what's called a p-value. This is the original sense of p-values, and it's the estimated probability of obtaining a more extreme estimate conditional on the treatment effect being exactly 0 for all units. And so what Fisher did was interpreted the p-value as a measure of evidence against the null hypothesis, and it's in units of probability, and so you don't have to it's unit free. But Fisher didn't have an alternative hypothesis in that framework. It's just evidence against the null of no treatment effect, and a lot of researchers who read Fisher's book felt the framework didn't give them enough because it didn't tell them how should I proceed as a result of having done this one experiment. And so Neyman and Egon Pearson picked it up and presented a different framework to try to address that criticism. And in that framework, researchers would specify 2-point hypotheses about the parameters. So like what we did today with Tibshirani and Price, hypothesis 1 might be that sigma is equal to 65. Hypothesis 2 might be that sigma is equal to 27. So there's only 2 possibilities. And then you calculate some statistic, the likelihood ratio has the most power, that conditions on the parameter values assumed by hypothesis 1 and hypothesis 2. So hypothesis 1, that log likelihood or likelihood goes in the numerator, and hypothesis 2, the likelihood implied by that goes in the denominator. And if you can choose a C like we did, such that you reject hypothesis 1 in favor of hypothesis 2 only 5% of the time when hypothesis 1 is actually true, then we say the procedure is well calibrated, or it controls the type 1 error rate. So this is where type 1, type 2 errors, where that vocabulary came from. And if you construct some rule for making a decision, like anytime the likelihood ratio statistic is less than C, we'll reject, otherwise not, and apply that rule over many, many decisions, you can be assured that you're going to be making the wrong decision only 5% of the time when the first hypothesis is in fact true. So this Neyman and Pearson framework does answer the question, or provides an answer to the question, how should I proceed having done one empirical study? but it's way weird. Like, why should we only consider two hypotheses about a parameter that can be any positive real number? And why is it that like we only worry about type 1 error rate and don't worry as much about type 2 error rate, type 2 error happening when we accept hypothesis 1, when hypothesis 2 was in fact true, when we accept that Tibshirani threw the darts when in fact Price threw the darts. But even if that seems weird, a guy named Abraham Wald here at Columbia in the 1930s, who was a very good mathematician, set out to prove rigorously that the Neyman and Pearson approach to making decisions was, a good procedure. And then when he sat down to actually prove the theorems, he proved something that was different than what he thought he was going to prove when he set out to write it. And he proved one of the most astonishing theorems ever, in my opinion. Biased, but whatever. And what he proved was that every rule for making decisions was either Bayesian, in the sense that we've been talking about, the limit of a Bayesian thing as the sample size goes to infinity, which never happens literally, or is dominated by some Bayesian decision rule. So what does dominated by a Bayesian decision rule means? That means the expected loss over decisions is no better than some Bayesian approach for any value of the parameters in the parameter space, and it's worse than the Bayesian approach for some value of the parameter in the parameter space. That's the sense in which dominated is defined in this. And if you look at that, and you might say, well, my n is always finite, there's always some Bayesian decision rule that's going to dominate any frequentist rule, I should be Bayesian. And this finding convinced Wald to become Bayesian, but he only told a couple of his family members about that, because it was not, it would have been professional suicide at the time for him to say, publicly that, okay, I'm Bayesian now. He just sort of wrote a book with this theorem and then kind of left it at that. If he had, Fisher would have written letters to Columbia to try to get him fired and, all that kind of stuff. Unfortunately, Wald and his wife died in an extraordinarily suspicious plane crash over India. And so he didn't live that much longer than that and did not really have too many more opportunities to actually, come out as a Bayesian, as it were. Question?
Could you elaborate on how Wald actually proved this? Because I feel like Wald's test with the concept of restriction matrix, transpose times the inverse of the information metric, that is the estimated asymptotic variance, times the restriction again, has the asymmetric.
But the Wald thing you're talking about is the Wald test. He has more than one thing named after him. I think is basically an instance of number 2 here. Making agencies, etc., were also unwilling to really embrace Wald's kind of astonishing result, and they made this Frankenstein combination of Fisher's framework and Neyman and Pearson's framework, despite the fact that no one advocated this, and neither Fisher nor Neyman had anything good to say about each other. And you see this with the way newspapers cover political parties, where political leader of one party will say something and then political leader of another party will say well, the opposite is true, and then the newspaper will say, well, it's got to be somewhere in the middle. Let's just combine these completely opposing statements. And you see that with anytime two people are making an argument and one says to the other, no, you're completely wrong, and then someone else says oh, can we all get along, or something like that. And it's not the case that the truth lies somewhere in between the extremes. It's the case the people at the extremes are starting with different foundational principles, and indeed under those principles what the other person is saying makes absolutely no sense. But instead of saying, oh, well, the truth has to be some combination of these things, you have to decide what your foundational principles are going to be. But people with no foundational principles decided to put this like synthesis together, where essentially they made hypothesis 2 in the Neyman and Pearson framework be an interval that is the complement of hypothesis 1. So this got put on 2 pages, which is unfortunate. But we have the null hypothesis that the parameter is some hypothesized value, usually 0. And then the alternative hypothesis is that the true parameter is not the hypothesized value. It's any number besides that. It could be 2-sided alternative, could be 1-sided alternative. But in any event, the alternative hypothesis is that the true parameter is in some interval of the entire parameter space that excludes one point, namely the one point hypothesized under the null. Then you do the sort of same thing where you get the distribution of the test statistic under the null hypothesis, control your error rate, etc. And then you can calculate it for the one test statistic you observed in your one realized data set that's randomly sampled from the population to see if that value is greater than or less than C, or equivalently that the p-value is greater than or less than 0.05 or whatever type 1 error rate that you want to specify. So no one advocated that, but it did not even, well, that by itself wouldn't have even really answered like the research practitioner's question, how should I proceed after having done this study? Because if the researcher rejects the null hypothesis that theta is like 0 in favor of the alternative hypothesis that theta is not 0, that would be completely insufficient to tell the researcher what to do, what to decide, how to act, what to conclude, etc. Because you need to know more than something is not 0. You need to know what it is, or at least have some approximation of what it is. And so this combined procedure that the journals fabricated evolved under some definition of evolution into the procedure that you see in practice, maybe not as much in the past few years, but over the past few decades, where if you fail to reject the null hypothesis that theta is 0 or whatever, then proceed as if the null hypothesis is true. And if you reject the null hypothesis that theta is 0 in favor of the alternative hypothesis that theta is some number other than 0, then you're allowed to proceed as if theta is equal to theta hat, the point estimate that you obtained from theta. So Fisher didn't advocate this, Neyman didn't advocate this, neither of the Pearsons advocated this. No frequentist could advocate this because it's in direct violation of frequentist principles, because theta hat is the realization of a random variable, and you're proceeding as if you specified it in advance as a hypothesis too in the Neyman and Pearson framework. And so this procedure that got codified in the journals doesn't have any good frequentist properties. And no one really advocated it, but it provided a guide for journal editors as to what papers to publish. And as a result, researchers didn't even bother submitting papers that failed to reject a null hypothesis, which related to the so-called file drawer effect, where only things that reject the null hypothesis get published. And it incentivized researchers to find some null hypothesis that could be rejected with the data in order to publish, something. And this, came to be known a variety of names. Today it's mostly called p-hacking. Find the null hypothesis that you can reject and then publish something. None of those are a really good foundation for scientific research. And all the time, there was a perfectly coherent Bayesian answer to the question, how should I proceed as a result of doing the study? Namely, make the decision or conclusion or whatever that maximizes your expected utility with respect to the posterior distribution. And Wald had already proven that that was basically better than the Neyman and Pearson approach. But no one at the time was willing to accept that, because the posterior distribution is going to have uncertainty. And that amount of uncertainty is going to depend in part on how much uncertainty there is in the prior. And different people could choose different priors, and thus they might make different decisions, even if they conditioned on the same data. And that was thought to be, unthinkable, subjective. Now, the fact that two different researchers that have the same priors and the same data could very easily make different decisions if they had different loss functions also didn't really seem to cause as much outrage. But the loss function is just as subjective as the prior is. And even two researchers that have the same prior and the same loss function might come to different conclusions if they have different data, which is oftentimes the reality, of the situation. And so inevitably there's going to be some amount of subjectivism in the decisions that get made. And the Bayesian approach basically tells us how to manage this. So what I think, and this is my opinion, is that the main reason the Bayesian approach didn't catch on with practitioners in the middle of the 20th century, people who didn't really care about the beef between, Fisher and Neyman and the rest of the English-speaking world, was that it wasn't possible to do on the computers that they had at the time outside of the people doing the Manhattan Project. It wasn't until about 1990 when this became a possibility to do with any generality for questions like social science. And by that time, we'd already had 50 years, if not more, where this frequentist, if you want to call it, procedure had been pretty well entrenched, not only in this, but with the textbooks.
I don't understand what exactly does it mean in the purified Bayesian form to maximize expected utility with respect to the posterior distribution. So in the example of the darts, we found out when we iterated one dart throw at a time that there was some posterior sigma distribution. Now, what would it mean in this example to maximize the expected utility?
Right. Say utility is like maximizing your dart score. What I was doing here, taking each of the values of sigma and calculating the optimal place to aim that would, for that value of sigma, and then I get a posterior distribution of optimal aim points, which would be my utility, and then I choose, take the expectation of that, and that tells me, where to aim. Same thing with, the poker problem, where Labat had to make a decision to maximize expected prize money, those sorts of things. So the actual process of it is reasonably straightforward. It's just, it depends on the prior and the loss function and the data, and not all of those are objective. Last problem, is basically just doing algebra and some calculus. You can go through it. All the solutions are elementary in this case. So the distribution of theta in question is actually the Pareto distribution, and it is naturally conjugate with the uniform distribution. And so if you condition on one uniformly distributed data point between 0 and theta, then the posterior distribution is also going to be Pareto with updated values of kappa and omega shifted around. So if you condition on n data points, that's like updating it n times, and then you can predict a future value based on the posterior predictive distribution that you obtain the same way as the prior predictive distribution. It's just using your posterior parameters for the shape of the thing rather than the prior ones. So you can look through that. Okay, so on to what we're scheduled to talk about for today, what Stan does. So what Stan does is create appearance of a conflict of interest by me as a result of working at Columbia getting a lot of grants to develop Stan, me using Stan outside of Columbia, and Columbia having a policy, which you can read about if you have not already. So where we left off on Tuesday, talking about what I refer to the ancient MCMC samplers, which are essentially those which were being used in the 1990s. Metropolis Hastings only requires you to specify the kernel, the numerator of Bayes' rule, But in the ideal case, only 22, 23% of proposals are going to get accepted. In order for those rare chance where the proposal is accepted to get a relatively big jump. But even the relatively big jumps might not be so big in absolute terms. You can get a lot of dependence from one realization to the next, even if your proposal is accepted. And the effective sample size can be essentially 0, or worse, the mixing may be so bad that the central limit theorem of Markov chain Monte Carlo doesn't hold in the first place. Central limit theorem in this context refers to if you were to run a Markov chain many, many times, what would be the distribution of the averages that you get from that Markov chain. If it holds, then it's going to have a finite variance and like asymptotically a normal distribution and stuff like that. But if the mixing is really slow, the central limit theorem might not hold at all. Gibbs sampling, you have to do more analytical work. Over the decades it's been done, but somebody has to work out what the full conditional distributions are from the joint posterior distribution. And if you can do that and say like, okay, theta 1 conditional on all the other thetas has like a normal distribution, you can draw from that. Theta 2 conditional on everything else has a gamma distribution. We have algorithms to draw from that. The jumps are always accepted, but they might not be very far. And if they are not very far, then the effective sample size can be low, and that tends to happen when the parameters are highly correlated, and thus the conditional variance is much smaller than the marginal variance for any parameter. And this is only going to work if all the full conditional distributions have forms where you have an explicit algorithm where you can draw from that distribution. The Bugs family of software starting in like 1995 overcame that problem to some extent and was sort of the first general purpose Bayesian software that people could use. It didn't require the user to work out what the full conditional distributions of everything were. That happens automatically with some pattern matching stuff. And when the pattern matching failed, it was some full conditional distribution that the software didn't know about. Then it had other ways of falling back to some other algorithm. They didn't actually use Metropolis Hastings, but they could have. Did something called slice sampling to obtain a draw from that parameter, and then you keep on moving on. And so this can be good-ish. It was thought to be good at the time, but when you fall back to some other like non-Gibbs sampler thing in the middle of a Bugs cycle through the parameters, when this happens, the effective sample size is going to get real bad, and the mixing is going to get real bad. The central limit theorem might not hold, etc. But this enabled, at least the Bugs language allowed you to express Bayesian models without any real restrictions other than you had to use proper priors. Now, one thing that you will see in the literature is that people, particularly back then, using Bugs, using JAGs, using WinBugs, etc., and then faced with this requirement that they had to do proper priors, would often do like normal 0 with variance like 1 million or 1 billion or something like that. That was kind of barely proper. So for any finite variance, it's going to be proper. And that allowed Bugs to run, even though that prior may be ridiculous to have a variance of 1 billion. And so you will see a lot of proper but absurd priors being used if you look at Bugs files that are out there on the internet. With Stan, or not so much Stan, but in the era of Stan, there's been much more of a shift to specifying what you think are realistic priors rather than trying to be improper. So how will we compare Stan to these? Like Metropolis Hastings, you only have to specify the numerator of Bayes' rule, and you can even ignore the constants in the numerator of Bayes' rule if you want to. Like Metropolis Hastings, unlike Gibbs, the proposals for the new parameters are joint rather than what's the full conditional distribution of something like Gibbs sampling does. Unlike Metropolis Hastings, but like Gibbs, proposals are always accepted. There's no rejection. And so also unlike prior predictive matching. All your proposals get accepted, so that helps keep the effective sample size high. Unlike Metropolis Hastings, but like Gibbs, you don't necessarily have to do any tuning of the sampler. Sometimes you kind of do. Unlike both of those, the effective sample size tends to be good, and it's sometimes greater than 100% than the nominal number of draws from the posterior distribution, because the first order autocorrelation in the expression for the effective sample size is negative. So the ancient MCMC samplers would always have positive first order autocorrelation and positive like the rest of the correlations. So this sum in the denominator here, although hopefully it converges to some finite number, it's the sum of a bunch of positive things. So the sum is positive, and you're dividing the nominal sample size by a potentially big positive number. What Stan achieves with its algorithm, the first autocorrelation should be quite negative. And so the subsequent ones may be positive or whatever, but you're combining like a fairly big negative number with some positive numbers. Anyway, the sum tends to be closer to 0, and the effective sample size tends to be closer to the nominal sample size. And sometimes if the first order autocorrelation is sufficiently negative and the subsequent order autocorrelations are not too positive, the denominator might actually be less than 1, in which case you get effective sample size greater than nominal sample size, and that's even better than independent draws for estimating expectations of functions that come out. Even more important, in my opinion, unlike both of those, Metropolis Hastings and Gibbs, Stan will produce warning messages when things are not going well. There's a tendency to ignore those, and that is very bad practice. So we haven't been able to completely prove all the properties of the algorithm in Stan. It's actually changed a few times over the years. But in practice, it's essentially the case that either Stan will work well, or you will get warning message saying Stan did not work well, and those warning messages will be like accurate. There's very few like false positive warning messages, and that is completely different from like the ancient and like other MCMC samplers that people are proposing these days. Main downside of Stan, at least perceived, is that unlike bugs, Stan does not allow the parameters that are unknown to be discrete. Not only do they have to be continuous, the posterior distribution has to be differentiable. There's some stuff you can do to get around that, but basically speaking, Stan is intended to work on posterior distributions that are differentiable with respect to all the parameters, which is a very wide class of models that you might want to estimate, but it's not all models. And among that class, with very high assurance, Stan will either work well or it will tell you from its own output that things didn't go well. All right? So what does that mean? Stan implements a variation of what's known as Hamiltonian Monte Carlo. So instead of just drawing from the posterior distribution of theta, conditional on the data, Stan is going to augment this, the theta variables, which you can think in the physics sense as being positional variables, with an equivalent number, let's say k, momentum variables denoted phi. And then it draws basically from the joint distribution of phi and theta, but integrates phi out to leave just a posterior distribution of theta given the data. And it's fairly easy to integrate out phi analytically because the likelihood function doesn't depend on phi. The likelihood is only a function of theta. Consequently, whatever prior you use for the momentum parameters phi is going to be the same as the posterior distribution, or the posterior distribution of the phi parameters is going to be the same as the prior. So you can sort of choose that to be whatever you want, and what Stan chooses is a normal distribution for phi with mean 0 and it can tune the standard deviation in order to achieve better effective sample size and fewer warnings. So anyway, the momentum parameters are just being drawn independently from normal distributions by default. And then with this idea of position and momentum, we're able to construct a valid Markov chain Monte Carlo process that is a physics simulation based on Hamiltonian physics. Now, you don't actually have to understand the physics, and I certainly don't. My understanding is that if you were an undergraduate physics major, this would be something you would be expected to understand, but it's not like rocket science. So Newton physics is too simple. Einstein physics is unnecessarily complicated for this. We're not talking about going at the speed of light. But in between that, Hamiltonian physics is basically just right for what we needed to, and Hamilton figured all this out in the late 1800s without a computer. But we're able to simulate Hamiltonian physics on a computer where the realizations of the momentum parameters phi push the location parameters theta to a new location in the parameter space that's endowed by a topology that has the log kernel of the posterior distribution that we want multiplied by -1. So the -1 is not a big deal, but you people's understanding of gravity is such that down is the direction that the gravitational force pulls. And so if it didn't multiply by negative, then gravity would be pulling you up, which could kind of make sense if there was a big mass above your head, but whatever. So the way down is defined for humans is like in the direction that gravity pulls. So what does this look like? If I can make this bigger. So here we have bivariate normal log density, but I've multiplied it by -1. So if I didn't multiply it by -1, it would look like this, which is sort of similar to what we saw before, but it actually is multiplied by -1, so I'll put it down like that. And then we have this location in this bivariate parameter space of x and y given by this green thing here. And so that is the current location of theta in this two-dimensional space, and the shape of the curve is the logarithm of the bivariate normal density multiplied by -1. And so if we then do the physics simulation, you can see it moves around basically according to something that looks like it might be reasonable physics, with the exception that there's no friction in this system. So in reality, there's friction, but if we're doing a simulation on a computer, we can have friction or no friction if we don't want friction, and we don't want friction here. So aside from it doesn't ever like slow down or stop, you know, this looks like it's behaving in a pretty predictable fashion if you assume that there's no friction. And it's basically moving around according to a normal distribution. You can also see that the denominator of Bayes' rule, which we don't know how to calculate analytically, would just affect like the location of the box up and down. It doesn't affect the shape of the curve, and consequently it doesn't affect the shape of how things move under Hamiltonian physics. If you go back one, stop, pause, whatever. Oh, now I'm stuck. This doesn't happen in actual Hamiltonian physics. No. Stop. Okay. If you go back to this, so we have the logarithm of the right-hand side of Bayes' rule and then multiplied by -1. So we can ignore that constant, and the main reason for that is because the physics thing involves the derivative of the posterior log kernel with respect to theta. But the denominator of Bayes' rule, or the logarithm of the denominator of Bayes' rule, isn't a function of theta. So the derivative of that with respect to theta is 0. So in a manner of speaking, like we don't know the denominator exactly, but we know how it would move. We know how it would change exactly, just based on taking the derivatives of the numerator, well, the logarithm of the numerator, with respect to theta. So it moves around like that. The algorithm in Stan, the original one, was actually called no U-turn sampling. So when it moves around that thing, the movement is actually deterministic. So how do we make this into a stochastic algorithm? What happens is like the theta moves around a little while, and then we stop it, and then we hit it with a new random draw of normal wind, basically, that changes its momentum. Moves around a little while longer, we stop it, and then we select among the places that the particle has been at according to the posterior kernel height. And so you get, it's actually a two-stage process or whatever, but we're basically doing multinomial sampling among the places where that little green thing has been since the last time we hit it with random normal wind. So it moves around, we stop it, and then we take as our draw for that iteration one of the places it's been with probability proportional to the posterior kernel. Then we hit it with normal wind randomly drawn from a different direction, moves around more. So that's what makes it random, but it allows the question, well, how do you know when to stop it? And what Hoffman, when he was a postdoc here, came up with a criteria, well, you should stop when there's a U-turn in the theta location, when it starts to come back to where it started from when you hit it with the wind. So when you hit it with the normal wind, it starts to move in one direction. And when it starts to make a U-turn and come back, basically in the direction it came, then it's not really efficient to let it continue go, because you already have a whole bunch of footprints of it going out. And then it like makes a U-turn and comes back like kind of in the direction that it came before. But you already have like a bunch of places that you could draw of it going out. So it's kind of redundant to also consider the places when it's coming back. So it gets hit with the normal momentum, randomly drawn from a normal distribution. It goes out. We stop it when it starts to make a U-turn. And then we take as our realization for that iteration of the Markov chain a multinomial sampling of one of the footprints it made on its way out, according to the height of the posterior kernel. And that gives you a totally valid Markov chain that's basically just a discretization of this continuous time Hamiltonian physics process that was derived a long time ago, and it involves solving a system of ordinary differential equations to tell you how the location and the momentum of the theta change over time depending on the shape of the thing that it's moving around in. Those ordinary differential equations can't be solved analytically, but there are at least one, perhaps more, really good algorithms for solving them numerically that are implemented in Stan. They require some tuning parameters relating to step size and whatnot, but those are tuned for you automatically during the warm-up phase. So by default, it's going to do like 1,000 iterations where it sort of tries to tune the step size and a couple other things in order to adapt to the posterior distribution that you're trying to draw from. Then those get frozen, and it continues, the tuning parameters get frozen, and it continues for another 1,000 iterations per chain that you then keep and analyze. And then by default, it's going to do 4 different chains. And so by default, you're going to get 4,000 draws from the posterior distribution, and you don't necessarily have to do any tuning in order to achieve this, although in some cases that can be helpful. So that's kind of the Stan algorithm, but when we refer to Stan, there's like a lot of different pieces to it under the Stan umbrella. So Stan is its own language. We've seen that like a little bit. There's a translator of Stan language to C++. that you never have to look at, but C++ can be compiled in a very optimized fashion by your C++ toolchain, assuming you can get that installed. There's a stan, well, it includes new algorithms like the one that I was referring to, no U-turn sampling, and also like some old algorithms for just optimization and stuff like that we're not going to talk about very much. It includes a math library that supports so-called auto-differentiation. So when I was talking about this, solving the system of ordinary differential equations, talking about the gradient of the logarithm of the posterior kernel with respect to theta, you might think, oh, I'm going to have to take all of these derivatives. You do not, because it is easier to teach a C++ compiler how to do calculus correctly than it is to teach a person. So basically, when the C++ code gets generated, it also includes instructions to the C++ compiler as to how to take the derivative of that thing. And that is what is known as auto-differentiation, which means almost all users of Stan never have to worry about those derivatives, but they are calculated very accurately in general and relatively quickly by the C++. So there's interfaces to the whole thing from R and from Python and some other things. We have a bunch of R packages that provide Stan programs and help you deal with the output. And then there's a large community of people by now who use, and a smaller community but still large, who develop, including some people who were in the QMSS program in previous years. So I explained auto-differentiation a little bit. You don't really have to worry about it unless you want to develop stuff. But basically, the auto-differentiation library in Stan is pretty much optimal for the task that Stan is mostly used for. TensorFlow by Google is another thing that is approximately as good, but not necessarily optimized for the same use cases, and there's some other ones out there. So what's the workflow? We're not really going to be doing this till April, but you write a program with a .stan extension that specifies the blocks and whatnot, says what parameters you want the posterior distribution of, what data you want a condition on, and in the model block, the binary from inside R, and then analyze the result of the draws from the posterior distribution. And we'll talk more about how to do those things next week in order to compare models, make decisions, things like that. So to sort of wrap it up a little bit, if you do bivariate normal and use the latest iteration of no U-term sampling, like I said, it's changed about 4 times since the original Hoffman paper. But anyway, you load up RStan. There's a file called bivariate or binormal2. It's up on Canvas that is doing the same thing that what I was doing on Tuesday with this 0.75 correlated bivariate normal distribution that we're drawing from. And you do that, it compiles, then it runs really fast, and we get good estimates of the mean of x and y, which are 0 in truth. We're getting good estimates of the standard deviation, which were 1 in truth, but we're getting an effective sample size that's like 3,500 on a nominal sample size of 4,000. 1,000 post-warm-up draws from each of 4 independent chains that were run. So that is a, like 80% or so in this case of the nominal sample size we're getting as the effective sample size. In contrast to what we saw on Tuesday, where Metropolis Hastings was like 10%, Gibbs sampling was like 30%, and the Bugsish program I wrote was like 20% on this very simple bivariate normal example. So we can achieve something much close to 100% in this case. A lot of times it actually exceeds 100% for some of the posterior margins. And the Metropolis Hastings and the Gibbs or whatever, like they work decently in this very simple case. Stan continues to work pretty well, even in much more complicated situations where Gibbs and in particular Metropolis Hastings start to do much worse as the models get more complicated. Stan, in a manner of speaking, can do better as the models get more complicated. And the reason for that, fundamentally, like ignoring the details of the physics, is it's utilizing the derivatives. It's utilizing the gradients. Metropolis, Hastings, Gibbs, etc., are only utilizing the level of the posterior function. And so by using more information and this physics rules for how to move things around in the absence of friction, it can move around the parameter space very quickly. It can mix very quickly. It's more likely for the Markov chain Monte Carlo central limit theorem to hold, and if it does, more likely to get a really good effective sample size. And if something goes wrong, there would be warnings right here saying this has gone wrong. And so that, in my opinion, is what makes Stan really good, and it's why starting next week and like for the rest of the semester, we're only going to be using Stan, not going to touch anything Gibbs, Metropolis, Hastings, anything like that. Question?
I wanted to ask about the output that we get. What does R hat stand for? Is it like?
We'll talk about this next week. This is a diagnostic of the convergence of the 4 independent chains to the same part of the parameter space. When the chains have converged, that number should be 1. And if you see it anything greater than like 1.01, you should be concerned that Stan hasn't been able to converge for the posterior that you specified, but there will probably be warnings to that effect. You will see we'll talk about this more next week, but you will see in the older literature, people say, oh, if it's less than 1.1, like it's probably fine. With Stan, it's like pretty much always just 1, and if it was even a tiny bit higher, I would be concerned. Because the Stan algorithm is so good that there's nothing that should stop 4 independent chains from quickly converging to the same part of the posterior parameter space and then mixing around from there.
So what does it actually measure? Can you like
it is a measurement for how much your posterior standard deviation could be reduced if you were to run this infinite number of iterations. So the scale factor. And so if it's 1, then you're basically fine to stop at some finite number of iterations as opposed to going on truly infinite number.
So what this tells us is that if we go till infinity, then our standard deviation should be 0. Wouldn't this always be the case?
So this should correspond to the true standard deviation, which is 1. What I'm saying is the fact that we only did 4,000 draws means that our estimate of the standard deviation has a scale factor given by this R hat, which is 1. So it's basically not changing at all. If it was like 1.1, 1.2, that's saying we could reduce our estimate of the posterior standard deviation by a factor of dividing by 1.2 if we were to run this out an infinite amount of time. You got a question?
Is that what we see? Like, is it the same thing as PSR and other software?
Yeah.
outputs?
Okay, so I have the reading for next week in this box that's holding up the door, which will now close. But so grab one of these on your way out. It's from a book by Andrew Gomez and some other people that's in the process of being published, and he wanted me to print those out so it doesn't end up all over the internet. But anyway, you're welcome to have a copy, but don't make a whole bunch of copies for your friends or anything like that.
Can we scan it in the phone?
What?
Can we scan it in the phone?
No.
No.